So my presentation is a bit unwieldy because I'm not zeroing in on a particular aspect of what we're doing. I'm trying to give a big, messy overview of a little bit about what we're doing in low-energy nuclear reactions, quantum computing, even some discussions about quantum thermodynamics, but mainly the discussions about the code theoretic axiom and the principle of efficient language and what that would mean if those things are true to a geometric, discrete topological quantum field theory. So this is our team right now. Some of you know Carlos Castro, Christy. Some of the guys live in different countries, and there's a couple people missing here, like Pascal. So our program here at QGR starts with this axiom that indeed nature is non-deterministic. She's certainly not an algorithm playing herself out, or at least we don't think so. We think that nature is inherently non-deterministic. But that leaves you two choices. You can imagine that there's some primordial random number generator for which you cannot explain its origin or how it works. So in some sense, it becomes your axiom, your religious starting point that you cannot prove. Or you can say, I don't know how it can be possible, but somehow the laws of physics allowed human consciousness to emerge without magic. And so what is the upper limit of emergent consciousness forward of us in space-time or in general? And could somehow there be some strange substance, of a choosing entity or a Planck scale measurement operator or something that does this primordial mathematical act that's analogous to measurement or the actualization of abstract information? So that then is the code theoretic axiom where you say, well, nature could certainly be a code, since a quasicrystal is a code derived by cut and projection from higher dimensional lattices, and that's a non-arbitrary geometric language or code, but then what operates the syntactical freedom within the code? Either you plug in your theory of randomness operates it, or you can say some other strange measuring operator, choosing operator of the code syntax operates it. So we try not to get too philosophical. We just have to not run away from that question because we're dealing with a project here which is trying to wipe the board clean and ask, well, what would be the most irreducible first principles theory of everything starting at the ground with no aggressive axioms? So anyway, then the principle of efficient language just says, all right, if nature is code theoretic, well, she probably wouldn't use some arbitrarily efficient code. She would probably use the most efficient code necessary to simulate these physical laws in this physical construct. So so we don't know if our quasicrystal code is the most efficient code, but if we could prove that mathematically, then we could say, well, if nature's a code, that's an axiom, then a principle is that she's an efficient code, not just any efficient code, the maximally efficient code. So that's the gist. Those two things guide a lot of our choices of what rabbit holes we can go down with our investment of time and money here. So it kind of starts with the cut and project Phazon walks. So your dynamical walks in a quasicrystal space, which can be looked at with a lot of algebraic types of formalism, such as moduli space algebras, C-star algebras, non-commutative geometry. But however you look at your walks, it's fundamentally guided by the walks or the walk rules in the higher dimensional space that projects to your projective space. And so that's a big deal for us, that aspect of our project, because everything kind of creates with that. Why would the cut window move like this in 8D or in the 4D quasicrystal that we use to create dynamism in our 3D quasicrystal, the quasicrystalline spin network? And then equally as fundamental is the Hamiltonian. So there's an object that you'll be learning about in Amrich's presentation and in Fong's presentation called empire. And that's the part of the code that in a given frame, a given code legal selection state on the graph drawing, so once you have one of those, there are these objects that you can register. You can register connections, points, or 3 simplexes in our case. You register anything as on, you force it to be on, then it forces things around it, but not everything. And so the things that it forces are called the empire, and the things that it does not force is everything other than the empire, where the syntactical freedom in the geometric code exists. So Emmerich has been working on the Hamiltonian approach from this very first principles idea of empires. So then there are 6 kind of tracks that I'd like to develop and set up grants for people or hire people and start working in these directions. One of them using the QSN and its mathematics and its Hamiltonian eventually. Amplitudes and gauge symmetry unification. So by using E8, we think we can recover, well, we know we can recover the gauge symmetry unification just by simple objects like Coxeter H4 folding matrix will allow you to recover E8 gauge symmetries from the projection of E8 to Elsner-Sloan's 4-dimensional quasicrystal. Anyway, then there's quantum cosmology. So we published a paper with Sergio Vaccaru on using quasicrystalline structures in quantum cosmology that got approved in in a good journal. Black hole physics, so Marcelo Amaral here, who is unfortunately not with us, he has done a lot of thinking and some work in quantum black hole physics. Quantum thermodynamics, which I know David's interested in. Quantum information, which ties it all into, I mean, the whole thing is information theoretic. So the quantum information is just ways that you can apply this to black hole physics and to quantum computing architecture. And then the QSN-based materials science, like the low-energy nuclear reaction stuff. And this is a couple preliminary problems that I wrote down, which is by no means exhaustive or vetted by the rest of the group. I just put down the efficiency proof. I think that's important because we have a pathway to mathematically prove that the QSN is the most powerful graph, topological quantum graph code. And I have to define a bunch of things. So I have to define what efficiency means, for example, but, which I'll do later in this presentation. But we know we have our definition of efficiency. What is the most natural algebra? Because there's so many complicated mathematical formalisms that we could train ourselves in or standardize ourselves, because some person in the group might be familiar with C-star algebras. Like I know, Mike, you know a little bit about C-star algebras. I don't. So what would be the most natural algebra? The Phazon code, when you look at it as a moduli space algebra, you know, is that a good way to go? The Phazon just means the dynamics in a quasicrystal. And then this formalization of this mathematical operator called the viewing vector, which just takes measurements or actualizes states locally. So for the last few years, we've been doing some novel research to grow nanoclusters in zeolite cages for application to low-energy nuclear reactions, also known as cold fusion, and quantum computing technologies. At very small sizes, clusters, monoatomic clusters, fall into quasicrystalline symmetry, which is icosahedral symmetry at small sizes, like 1.5 nanometers, for example. It's going to be icosahedral. And then we've had some very sensitive calorimetry analytics that we're proud of. That took us a long time to develop. We approach our whole approach to materials science. It's really a synthesis of some novel nanocluster physics and basic crystallography and chemistry. So quasicrystals were only discovered in 1984, which is interesting because it's an important phase of matter to be missed, completely not seen until 1984. It's interesting. It means a lot of professors, a lot of people out there, they really don't know about it. It's too new. I think there's about 65 people in the world who work full-time on quasicrystal mathematics or physics, and 25% of them work here. So it's a very small community. And so whenever we go to somebody in the LENR community, the quantum gravity community, or quantum computing community, and we mention, hey, haven't you even thought about quasicrystal mathematics? And it's not like they ever have any criticism. They go, wow, actually, that's really interesting. No, I never thought about it. It's too obscure. It's not difficult. It's simple stuff, but it's arcane when such a small number of people know about it. So that phase, the quasicrystal phase, it's only seen with a careful annealing recipe with particular ratios and combinations of elements. Then you have to stop it, anneal it at exactly the precise temperature, like scanning through a radio dial very, very fast. And at this one particular station on the spectrum, you lock it in. So it's not surprising how quasicrystals were missed, because the guy discovered them accidentally. Danny Shechtman wasn't looking for them theoretically. He just accidentally saw this in the electron microscope, more or less. He was trying to fabricate, alloys. And this phase is driven by optimized tunneling density and frequency that's actually not allowed by classic thermodynamics. So of the 300 or so quasicrystals discovered so far, all of them that I've seen at least have golden ratio-based atomic spacing. There are quasicrystals that are mathematically possible that don't have the golden ratio spacing, but the ones in nature the 3D quasicrystals in nature that I've seen are all golden ratio based, because any arbitrary irrational angle of a hyperlattice slice to lower dimension generates a quasicrystal. But the ones nature does are not just any arbitrary angle. They're these special angles relating deeply to the root vector polytope symmetry of the hyperlattice, which is where the golden ratio then comes into play in the projective space. So each 3D cluster of atoms can be decomposed as a network of one-dimensional quasicrystals, which you can think of as sort of linear aperiodic necklaces stretched out in a straight line, where the beads of the necklace are deep and narrow double well potentials that each approximate the ideal Dirac delta function double well potential, where the probability for quantum tunneling goes to 100% probable because the wells are so deep and so narrow. So of course these physically are not Dirac delta function double well potentials, but they are extremely deep and narrow double wells, and so the probability for tunneling exponentially increases in these systems. So in these quasicrystal states, as opposed to a FCC crystal lattice, a double-digit percentage of these deep, narrow energy wells at any given moment is vacant, creating a temptation for neighboring atoms to tunnel to that coordinate. So it's a very bizarre thing, because normally in nature, you don't see entire atoms tunneling with real-world probability. But in these systems, you exponentially increase the probability even for entire atoms to tunnel. So, and again, the tunneling dynamism is Phazon dynamics, and they work in waves, like they're quasi-particles. So atomic arrays in this optimal phase tunnel with virtually no energy to vacant wells via an action called the Phazon hop. And quasicrystals are just not understood very well. I've been going to the conferences for the last 7 years, mostly with Fong and some old members of our group. And we watched the PowerPoint presentations for a week in these conferences, and about 50% of the presentations are reporting a new anomaly. And there's anomalies, there's entire books on the optical anomalies in quasicrystals. There's electromagnetic anomalies. There's thermodynamic anomalies. And there's quantum mechanical anomalies even. There's behavior that's not easily explained by applying ordinary quantum mechanics. So it's a treasure trove of new physics. World famous David Chester said, since no theory of non-equilibrium thermodynamics is agreed upon, many scientists are stuck in old paradigms stemming back to classical equilibrium thermodynamics. A proper understanding of quantum thermodynamics is needed, something that Carlo Rovelli passionately argues as well. Such a theory could provide breakthroughs for how humans process energy in dynamical systems, such as maybe LENR or quantum computing. If everything is created out of the quantum vacuum, perhaps a new geometric understanding of quantum gravity can help to create and control causal entropic forces based on resonance and entanglement principles. So our published papers have shown experimentally and theoretically how resonance, this is published with some of the guys in the Ukraine who work for us, papers on anharmonic, special restrictive anharmonic oscillators related to the golden ratio where quantum tunneling exponentially increases. So, as I said, to achieve these special exotic states, you've only got two ways that you can arrange things, in time and in space. So it's seen from this visualization that these localized anharmonic vibrations, which, by the way, you can think of these special anharmonic vibrations as quasicrystals over the time domain. So they're orderly, and they're made of a finite set of frequencies and amplitudes, but it's a code because it's not chaotic and it's not periodic. So it's this bizarre thing in the middle. And this is a quantum molecular simulation of a cluster of palladium atoms, which is the subject of our focus with LENR. This is just a small selection of about 100 of the best peer review papers on cold fusion. In fact, cold fusion being real, it's well known to be real. It's now an accepted entrance to the growing list of physical anomalies in nature that are not allowed by current theory. Anomalies that are not explained by quantum mechanics, thermodynamics, or anything else. Our theory for how cold fusion works explains the experimental evidence better than any of the other theories. In a way, this is the experimental evidence. These are the nuclear byproducts that resulted in each of these published studies. And all the other theories I've heard of just focus on explaining hydrogen-hydrogen or deuterium plus deuterium fusion, and they just conveniently ignore how every single published result on cold fusion, in addition, shows evidence of a heavy element and a light element nuclear fusion event. And they're not explaining that. So our model explains that. So the Cold Fusion Conference in Padua, Italy, that I last attended, had all kinds of people there. It was Larry Page's brother from Google, NASA, the government of Brazil, Mitsubishi, MIT. So not one single presentation tried to demonstrate that cold fusion is an actual phenomenon. That would waste the audience time. It was just presentation after presentation trying to struggle with what in the world could be the physical theory, the new atomic physics that allows this unexplainable overcoming of the Coulomb force to be real. And there's no agreement. There's not even any good theory that seems to have a 15% consensus in that community. So, and without a physically realistic theory to explain some anomaly, it's virtually impossible, other than by freak accident, to discover how to potentiate that anomaly towards the physical limit. And so you might say, well, if cold fusion is real, Klee, and it's 500 people in these conferences, how come it hasn't changed the world? And the reason is because it's a pathetic result. It's a real result, but it's still cheaper to dig soft coal out of the side of a mountain and stick it in a furnace and let it give you energy, And that's a big challenge because coal is not like mining for diamonds. It's really cheap to scoop coal out of the earth. So These guys don't know how to reliably predict. They don't know how to reliably create the result. Sometimes it happens, sometimes it doesn't. And they don't know at all how to potentiate the result. And I think our program will allow it to be potentiated at the limit. Anyway, so let's talk about the golden ratio a little bit. In Paul Davies' non-quantum gravity equation, just using classic general relativity and classic thermodynamics, the golden ratio is the precise point where a black hole's modified specific heat changes from positive to negative. And in Carlo Rovelli's equation, the golden ratio is the lower bound on black hole entropy. And in our equation, which is written by Marcello, who's not here, the golden ratio relates the loop quantum gravity parameter to black hole entropy. And so when you see this simplicity here, it makes you confident to at least play around with the conjecture that maybe nature at the quantum gravity scale is using this very powerful mathematical number, because there's no other ratio in mathematics where you have this fractal self-identical quality where the ratio itself, the long part to the short part, is the same ratio as the long part to the sum, the whole of the long and short. That reversibility allows for physically important results. Any n by n binary matrix has as its most probable non-trivial eigenvalue the golden ratio and -1 over the golden ratio. And we have reduced Pauli and Dirac matrices to binary form to draw out a deep connection to quantum mechanics, trying to focus on this golden ratio as this fundamental constant, if you will, of nature. In 1993, Lucine Hardy of the Perimeter Institute discovered that the probability of entanglement for two particles projected in tandem, which is the simplest, it's two electrons moving at the same velocity on the same one-dimensional space away from each other. So you can't get any simpler relationship between two massive objects than that, right? And I mean, you could try to do it with quarks, but that would be tricky, right? In this most simple relationship, the probability for entanglement is this golden ratio number of phi to the -5, which is interestingly reminiscent of the so the probability of you finding one of these vertices in the Penrose tiling, which is like one of the quintessential quasicrystals. So if you were to randomly select vertices, the ratio of probability of finding any vertex, there's 7 vertex types. So each one of the vertex types, the probability is this. But the numerator maxes out at phi to the 5th. And so these are the vertices that are just the valence rank or the degree of the vertex. So these 7, so you could have one vertex that's like this, right? Another vertex that's like this. So if you're going to try to build particle physics and quantum gravity essentially out of graph theory and vertices and the connect valence ranks, you're going to be dealing with probability theory. So it's interesting that you get this. These results were experimentally confirmed in 3 separate peer-reviewed studies from 1993 to 2009. And then Marcello here, he argues that this number represents the fundamental limit of non-locality in nature. And then in 2010, a multi-university team of scientists found an E8-based golden ratio signature in solid-state matter. So not just any golden ratio expression, but a golden ratio expression that relates to E8, and I'll show you some of those in a bit. So the arc cosine expressions for the 8 root vector generators of the E8 lattice correlate. So you can generate the root vectors with tetrahedra. So if you just take tetrahedra to construct, because since the E8 lattice can be built entirely of regular tetrahedra, if I gave you a big stack of them and allowed you to rotate the tetrahedra into higher dimensions from one another, you could build out the E8 lattice with just that shape. And so how those tetrahedra are related to each other looks like this. So these are the arc cosine values, and you can see the golden ratio showing up here. So using one or more of these values to rotate tetrahedra from one another, essentially you construct the E8 lattice, or you could construct just the Gaussian polytope, the root vector polytope. So the root vector polytope angles are really simple, right? They're 60, 90, 120, 180 degrees. The root vectors there look extremely simple, but they are constructed, if you want to construct them that way, from tetrahedra using golden ratio angles. Now, based on the work done by Suresh and Koga in 2001, Horovska showed the atomic radius of hydrogen in methane to be the Bohr radius over the golden ratio. And then there are a half dozen elite particle physics journals that allowed papers arguing the theoretical and experimentally supported value of one of the most important parameters in the standard model, which is the Cabibbo angle, is arctangent 1 over phi cubed. And then our group recognized that if those authors are correct with the Cabibbo angle, that it seems that the Weinberg angle may be the square root of that, the arc sine of the square root of that same value. And that fits tightly within the experimental bounds. The KAM theorem is used widely in dynamic systems physics, from astrophysics to particle physics to fluid dynamics of space-time and electromagnetism, really any system related to tori and vortices. And statistically, vorticular systems with inner to outer curvature ratios that are irrational are more probable than ones with rational ratios. So then there was a derivative work, another paper, that showed that of all irrational ratios based vortices, the probability, the magnitude of the probability for finding one or for its survivability under perturbation maps to the rank of its irrationality, of the irrationality rank of that, of the geometry of that vorticular form. Now, this makes the golden ratio-based toroid and vortex physical systems in nature the most probable, the most likely that you will find them, because they survive more. And the reason for that is because of the nature of the golden ratio. The golden ratio is the only irrational number whose continued fraction is expressed with just ones. And that makes it approach its convergence at the golden ratio more slowly than any other continued fraction approaches its convergence. And that is how you mathematically prove or define the irrationality rank of a fraction. So therefore, because it's proven that the golden ratio is the most irrational of irrationals, you plug it into the KAM theorem, and you start seeing a deep relationship of the golden ratio to fluid dynamics. Now, when speaking of atomic ensembles as a code-based topological quantum network of deep and narrow double well potentials, some occupied, some not occupied, it is trivially true that only golden ratio energy well spacing allows such nanoengineering to arrive at the limit of non-local quantum correlation. So, code theoretically, this is the non-zero limit of freedom of the spatiotemporal letters. So when you think about a geometric code or a code in time, you can think about it the way you'd think of any language or code. You would have to realize that, well, you can't have just one letter, right? You can't make computer code out of just zeros. You need at least 2 letters. And by some definitions, you can start ranking languages in terms of their generality and their power by the quantity of symbols. For example, for a given task, let's say I've got a binary code with 2 letters, and I've got another code with 1 million letters. Even without getting mathematical about it, you can kind of get the idea that the number of letters. So you want to, in atomic ensembles, you don't want to go all the way to 1. You don't want to allow it to go to its lowest entropy, because then it'll collapse into a crystal state where each atom is essentially trapped in an electromagnetic trap, and it can only barely oscillate around its bottom of its energy well. And 100% of the energy wells are occupied. So there's just no freedom. It's not a code. And so a slight deviation, so this is a Fibonacci chain here, right? That distance is 1, and that distance is 1 over the golden ratio. And so when you start crossing Fibonacci chains to make 2-dimensional and 3-dimensional quasicrystals, the golden ratio allows you to have non-arbitrary closeness to define it properly as a quasicrystal. And to define a code, you have to have a finite set of letters. Whether it's a code in time or a code in space or both, a code is defined as a finite set of symbols with rules that also have freedom in the rules, syntax. You have to have those 3 elements to be a code. So anyway, so if you, so this is not a code, this is a code. This is a slight alteration of the angle. So you infinitesimally deviate from this angle, and you start introducing more letters into the code. That is, the distances between your energy well bottoms for each atom that's occupied and non-occupied, it takes on arbitrary values, and it just kind of explodes into this messy, chaotic dance of energy wells and atoms. So, and here also what happens is where you have all this experimental evidence of quantum long-range order, quantum tunneling explodes, topological quantum correlation explodes. You get these strange states like special Rydberg states. All of that collapses and decays when you move away from the quasicrystalline phase. So these simple concepts from off-the-shelf quantum mechanics, such as the Dirac delta function double well potential, and just basic thermodynamics, leads to a deduction. Nature provides a limit of quantum correlation in a topological net. Take 100 atoms and ask yourself, is there some way to arrange those atoms in time and space that reaches the theoretic limit of quantum correlation? And the answer should be yes, because everywhere we look, there are limits in nature. And so our program suggests that the limit is in the arrangements over the time domain and the space domain as quasicrystal structures. And just as a binary code is universal as a general code, optimized quantum computers based on spatiotemporal code theory as Fibonacci anyons expressing themselves non-deterministically with their syntactical freedom in a network of qubits, which you can manipulate, by the way. It's part of our program with Cambridge Quantum Computing. You have a universal limit for quantum computing. And that means that even though Google has one approach to quantum computing that they're gambling on, and Microsoft has an extremely different approach, at the end of the day, when the dust settles, the future of technology is going to use the optimal approach. And we think that Microsoft is closer to the optimal approach because they're hanging their hat on Fibonacci anyons. So what we're doing in our program is we're going to derive a geometric physical expression of Fibonacci anyons, and as opposed to how Frank Wilczek invented Fibonacci anyons as more of an abstract mathematical tool for particle physics. Now in quantum computing, they're using it also as an abstract mathematical tool, but they're getting into playing with how to arrange atomic ensembles in phase space and in spatial space. So there's a huge market opportunity to exploit any intellectual property going after this limit, which, as I said, would become the default formalism used by all efficient quantum computers. So in summary, the objective is to nano-engineer for the network of double well potentials to make a quantum computer, wherein all energy wells are of equal depth and width, and all spacing between wells is only of 2 spatial letters or lengths, and where a double-digit percentage of the wells are vacant at any given moment. So naturally, this reduces the vectors for each tunneling event to 5 in 2 dimensions, and generally 6 directions in 3 dimensions, except in the QSN case, our quasicrystal. So unlike a deterministic algorithm playing itself out, or a non-deterministic random ontology where particles can appear in quantum mechanics literally at any coordinate in x, y, z, t. A code is a massively restricted idea compared to the random view, which has very little restriction. But our view is massively free compared to the deterministic view. So we're in this middle ground where we like to be restricted because we're code theorists, but we need a little bit of freedom because we need that syntactical aspect to define it as a language. So a code is just a finite set of 2 or more symbols with ordering rules and syntactical freedom. Quasicrystals are geometric codes that play out on highly restricted networks of deep and narrow double well potentials that, if you like, you can call that the possibility space. So when we look at a correlation graph of entropy to temperature, we see a relatively smooth line. So here nature appears to be rather classic. The second law deals with spatiotemporal freedom of particles, of course, where high freedom is equal to high entropy. Now this term freedom is the same meaning as I mean when I say freedom in syntactical freedom in a code. It's spatiotemporal freedom in a geometric code. So this includes codes such as DNA and other quasicrystals. A code is a finite set of 2 or more symbols with syntactical freedom. So what makes a good code and what makes a bad code? Generally, powerful universal codes have a minimalistic symbol set and very simple syntactical freedom. For example, if one imagines 2 codes and one has 1,000,000 symbols and the other one has 2 symbols and very simple syntactical freedom, if they're both expected to simulate the same physical system, generally one would expect that the simpler code would be more computationally efficient. So the principle of least action and Noether's second theorem, of which it is just a special case, indicate that nature is interested in efficiency. And if nature computes, it would probably use an efficient code, as I said. Spatiotemporal codes use atoms or other objects in space-time as their letters or code symbols. However, it's more like a code in the game of chess, where the code rules and the freedom play out in a controlled space, where the code symbols, such as adenine and DNA, can only appear at certain locations in the possibility space that's fixed, like the way that the possibility space of where chess pieces can be is fixed. But there's rules and freedom in chess. The Penrose tiling, as well as other 2- and 3-dimensional quasicrystals, have been observed in nature as 3D networks of atoms. So in this case, if the atom is here, it cannot be here where the red dot is, and vice versa. So you can think of both the red dot and the blue dot as the possibility space where an atom can be. And so each of these 2 positions is legal in terms of the syntax of the Penrose tiling language. So let's do a thought experiment. Imagine that we have an alloy, a binary alloy, at some absolute 0 temperature. Now let us say its spatiotemporal freedom can be expressed as f factorial, and that it is approximately possessing 0 spatiotemporal degrees of freedom, or it's literally having 0 because it's at absolute 0. So here, of course, f equals 1, and then so therefore f factorial is trivial. It's just 1. So there are various ways to express the exponential increase of entropic combinatorics or interactions. And so I'm just using the factorial value here more as an analogy for the sake of simplicity as to represent the idea of the actual exponential algorithm that defines the logarithm of the entropic spectrum. So the crystalline state of this alloy cannot be a spatiotemporal code, as I said, because it is a system of electromagnetic traps with no approximations of Dirac delta functions. It's analogous to trying to code with just zeros instead of zeros and ones. The symbol set is too small at 1, and the syntactical freedom is essentially 0. Experimentally, its non-local quantum correlation magnitude is very low when we measure long-range order, entanglement, tunneling, etc. So let's heat things up. So now we have an amorphous alloy. We open up a disorderly array of energy wells with a massive number of different depths and widths and distances between them and directions between the two energy wells. So the lines running through nearest energy well bottoms explode right away, right early, into trillions of different directions with the very smallest of samples. Its non-local quantum correlation magnitude is very low. In other words, the quantum correlation magnitude exponentially drops very, very early as you increase the temperature, as you go up in the entropic scale. So it is because this code has exponentially higher spatiotemporal symbols, or degrees of freedom, that makes it a virtual anti-code. As long as there's a finite number, it's technically a code, but because of how it exponentially explodes, it becomes a virtual non-code. It becomes classic looking very early on. So here, if we say our spatiotemporal freedom magnitude is 50, right, our combinatoric value for all spatiotemporal objects or symbols and the interactions thereof is about 10 to the 32. So as we bring the temperature up, we increase the spatiotemporal symbols and syntactical interactions toward infinity. This is as f grows along this approximately linear algorithm. Okay? So all of these phases from 0 temperature on up behave classically more or less, except for the quasicrystal phase, which behaves as a topological quantum net code. So the crystal phase, again, isn't a code because it only has one spatiotemporal freedom, and none of the other phases are codes, at least not efficient codes, because even at temperatures not far above absolute 0, we had an exponential explosion of spatiotemporal symbols and syntactical complexity that make those phases virtual non-codes. So why are there thousands of reports in the literature on thermodynamic, photonic, and quantum mechanical anomalies in quasicrystalline phases of matter? Well, it's because at this phase, this is the phase which is at what you can call the non-zero limit of spatiotemporal freedom, which is 2. So instead of having just one letter, you have 2. And 2 factorial is not a big number. So it is at the maximal limit of code theoretic efficiency. As you go above 2 to 3 to 4, then, of course, you start exponentially changing the physics. So, and because deviations from the limit explode the combinatorics, making the code exponentially less efficient with the slightest alteration from the non-zero limit, it's difficult to produce or to even notice this phase of matter in the lab. So this is all a very superficial overview of concepts that I'm going to be sharing. But if there is one simple way of expressing the key concept of what I just talked about on quantum computing and low-energy nuclear reactions, it would go like this. The summary would be, the quantum gravity view does not allow for a fundamental distinction between a particle coordinate change, that is a tunneling event, versus a smooth change of coordinates where a particle traverses an infinity of coordinates between A and B. And let me give you another example besides tunneling. Let's say one interpretation of quantum mechanics allows you to think in terms of the Bohm pilot wave view, or another view which allows us to say that in the orbital for some trapped electron, it's approximately at some radius. And then at the next energy level, it discretely changes to another energy level and another radius. So we don't like to imagine that it gradually progressed through an infinity of radii between those two coordinates. We like to imagine the notion of the quantum leap, where it just simply is then it was here and now it is there. Similarly, with a tunneling event, you can invent these crazy hand-waving ideas that because you want to insist on classical motion. So you say, okay, the particle on one side of the barrier somehow borrows energy from the environment, and then it uses that energy to muscle through the infinity of high energy coordinates between A and B, and then voila, it's on the other side of the energy barrier, and it somehow then pays back its debt. Well, that's a hand-waving way to sort of force classic motion into the idea of the quantum tunneling event. But a simpler way is to take the quantum gravity view and say, no, every change of coordinate at any energy level is always an integer multiple of the Planck length. Instantaneous pixel changes, like on this monitor, where it is here, and then it can only be at some integer number of pixels at another coordinate. So then number two, accordingly, if all coordinate changes are discrete, so then all coordinate changes in a physically real graph drawing formalism. So we don't do graph theory around here like loop quantum gravity, where it's on a spaceless or abstract graph. We just do it on a graph drawing. So that way we can work in moduli space algebras in actual arrays, aperiodic arrays of points as a possibility space, and then discover the algebras and rules there. So anyway, that's basically what I said about integer multiples of the Planck length. So then when one engineers with chemistry or nanoengineering an energy landscape where atoms have massively restricted degrees of freedom, but non-zero. So you push them as close to the zero limit as possible, which is just barely above the crystal phase in the entropic spectrum. Then you achieve the non-zero limit of spatiotemporal freedom, and you get very exotic physics. So at that phase, entire atoms are experimentally known to tunnel with remarkably high probability. Here, too, is the phase where quantum entanglement of any number of atoms achieves its natural limit, making it an ideal topological neural net. So such a net is quantum mechanically described by Fibonacci anyons, the key tool used in the Microsoft approach for quantum computing. And this is a mathematical limit that I think is provable by geometric first principles. And if nature were non-smooth and interested in efficiency, she should use this construction at the Planck scale, if we can prove it. So let's just say hypothetically later this year we can prove something about the QSN, then we could say, well, if nature were a code, then she should be using this one, because by first principles you can't get a topological quantum graph drawing that has a higher average valence rank or have a higher rank of connectivity than this graph. This is our mission statement: to discover the geometric first principles unification of space-time, energy, information, and consciousness. So why first principles and why consciousness? Because we don't really want to do philosophy around here. We're not forced to think about consciousness for that reason. But why first principles and why consciousness? Well, as far as first principles, a successful unification theory can explain things such as the gauge symmetry unification of the standard model particles and forces with gravity. That would be successful, but it wouldn't explain everything. But unless it's based on first principles, it's not likely going to explain the magnitude of the speed of light or give us the actual values of the fine structure constant, the gravitational constant, or Planck's constant. Currently, rough approximations of these values are plugged into unification models like the standard model with no deeper actual explanation. And furthermore, we don't even know what these values really are past the fourth place after the decimal. So the code data values are weighted averages from 6 disagreeing experimental approaches for things like the gravitational constant. So if you say, all right, so all of these approaches are decent, but if one of them is more accurate, wouldn't the other less accurate ones be contaminating the value of the first one by just averaging it to a less precise value? Well, the answer is yes, of course. And so you can then say, all right, well, to play it safe, all we can say with experimental certainty is that these values are what they are to the 4th decimal place. And anything after that where they start deviating, we just don't know. So that's why first principles. I want to know why I want to know the analytical expressions for the constants of nature. And I want to know why they are those analytical expressions. Not just, I don't want to just unify things. I want to know everything fundamental by first principles. So as for consciousness, whatever that word means, I don't know what it means. But whatever it means, it boils down to the measurement problem as far as why we have to deal with it in terms of seriously wiping the whiteboard clean and trying to understand first principles things. Werner Heisenberg said, was it utterly absurd to seek behind the ordering structures of this world a quote-unquote consciousness, see, he didn't know what it means either, whose intentions, whatever that means, were those structures, those physical structures. So think down at the Planck scale. So that's very, very deep what he's talking about. And he was also very worried about a first principles explanation for turbulence. He says, when I meet God, I'm going to ask God 2 questions. Why relativity and why turbulence? And I really believe that he will have an answer to the first one, but that even God won't know what causes how to explain turbulence. So he was saying he was really bothered by turbulence. And Richard Feynman was really worried about it too. He says turbulence is the most important unsolved problem in classical physics. Now, we expect physics on the quasicrystalline spin network to model all fluid phases from irreducible geometric first principles, including any turbulent phase, from simple first principles related to nothing more complicated than the Pythagorean theorem, just the first principles of projective geometry. So it'll be a quantum superfluid, the way that the QSN behaves dynamically. And Physics Nobel laureate Frank Wilczek has the most concise quote in this idea of consciousness at the Planck scale. He says, the relevant literature on the meaning of quantum theory is famously contentious and obscure. Like, people are still arguing about it today, and there's no consensus. And he says, I believe it's going to remain this way until somebody constructs, within the formalism of quantum mechanics, a quote-unquote observer. So he doesn't know what observer means. In other words, a model entity whose states correspond to a recognizable character of conscious awareness. Again, whatever that is. Andre Linde, who's a co-founder of inflationary Big Bang theory, says, maybe it's going to turn out, with the further development of science, that the study of the universe and the study of consciousness will be inseparably linked, and that you're not going to see progress in one without progress in the other. And then John Bell said, speaking of this subject, this weirdness, he says it's likely that the new way of seeing things will astonish us. We don't have the new way of seeing things. Like, we don't have a first principles theory. It's all still all quantum mechanics is this statistical, this probability theory, but it doesn't tell us why. Like, why? Why those probabilities? Why is nature behaving this way? So Erwin Schrödinger said, the stuff of the world is mind stuff. Arthur Eddington said, we don't find obvious evidence of life or mind in so-called inert matter, but if the scientific point of view is correct, we're going to ultimately find that, at least in some rudimentary form, all throughout the universe. I get the idea he's talking about at the Planck scale, because he's talking about inert matter. J.B.S. Haldane said, mind, or something of that nature as mind, must exist throughout the entire universe. And then Huxley said, the laws of physics leave a place for mind in the description of every molecule. In other words, mind is already inherent in every electron, and the processes of human consciousness differ only in degree, not in kind. So Freeman Dyson said, that which we experience as mind will, in a natural way, ultimately reach the level of the wave function and of the dance of the particles. There is no unbridgeable gap or barrier between any of these levels. It is implied that, in some sense, a rudimentary consciousness is present even at the level of particle physics. And David Bohm said, how physical processes create a subjective sense of experience or quote-unquote consciousness is unknown, which is true. And then John Conway and Cochin's free will theorem, which is a very mathematical approach, attempts to logically prove that if it is a true statement that humans have free will, which interestingly enough, the majority of physicists think that they have free will. Some of them think that they don't, but that's the minority. So they try to say that anybody who thinks they have free will, by logical deduction, fundamental particles such as an electron must logically have free will. Again, hard to define consciousness, hard to define free will, but there is something that has to be dealt with ultimately because of the measurement problem. And it's the measurement problem that makes all these guys say the quotes that they said. And yes, you can talk your way around the measurement problem, and I've heard explanations that require no notion of a measuring entity, okay? But those are also not consensus views. So non-subject matter experts, physicists who are not subject matter experts in this hard problem issue of fundamental physics, they often tend to blow off the measurement problem because they don't have a deep understanding of exactly how serious the problem is. Because our program insists upon irreducible first principles, we don't have the liberty of trivializing the measurement problem, just as we are not satisfied to merely unify the measurement values of particles and forces without explaining their exact values from first principles. And we do not subscribe to all of the postulates of the Copenhagen interpretation of quantum mechanics. However, we do appreciate the intuitions of the Copenhagen interpretation insofar as its implication that there must be some notion of a quantum scale measuring or choosing entity to actualize the physically real events and coordinates from an abstract possibility space via some form of some mathematical operator that you can say measures or observes or actualizes or chooses the syntactical freedom. So we arrive at the measurement problem in a different way than via the Copenhagen interpretation, a way that does not restrict itself to human-level measures or observers. It starts with ultra-conservatism, reductionism, and Occam's razor. The deduction that forms our code theoretic axiom essentially works like this. We think it's aggressive and speculative to presume energy is something other than information. The more conservative view is that of Wheeler, Tegmark, Stephen Wolfram, and all the other people who say, look, we can invent this hand-waving thing that energy is something more than information, but the safer view, but until we can come up with something concrete, is just to realize what it is, information. So axioms, of course, are the place where kind of science ends, where explanation ends, and a physicist or a mathematician has to choose some ontology that they cannot prove, some axiom. So people like Tegmark stop at the notion, the axiom, that information just is. He doesn't know how it comes to be. So that becomes Tegmark's unprovable axiom, the idea that he has without any explanation other than it just is. So this is Neoplatonism. That's where the notion of something foundational, such as energy, it just simply exists without explanation. The end of the scientific inquiry, and in a way, the beginning of a sort of religious faith, the faith in your physical axiom. So how do we go beyond the axiom that information just is and penetrate deeper into scientific explanation? Well, we can start by defining terms and deducing. What is information? I suggest information is meaning conveyed by symbolism or symbolic language. That's one popular definition of information. There are others. But that's the one that I'd like to use to go down this rabbit hole with you. Now, what is a symbol? Well, a symbol is an object that represents itself or something else. This can represent the square, if we say it does. That's pretty subjective. Or this equilateral triangle can represent itself. That's a little bit less subjective. Plus, in this case, as opposed to this case, there's inherent meaning by first principles of the meaning, like the area, the equidistant nature of the 3 points in flat space, the magnitude of the connections all being the same magnitude. So these are inherent in the symbol itself. Now, what's an object? Well, set theoretically, we can say that an object is just anything that can be thought of. Only self-referential symbols have virtually no subjectivity and possess implied meaning in their form by first principles. For example, I could use the equilateral triangle to represent change in a version of the delta symbol, and that's highly subjective, where the meaning is not inherently implied by the symbol itself. But when I use the equilateral triangle to represent itself, the meaning of the 2 simplex as the equidistant array of 3 connected points in flat space is inherent by geometric first principles. So the symbol itself contains logical, non-subjective, geometric, mathematical truth by some first principle that you adopt. And now, what is meaning? Well, meaning is a symbolic relationship. If you keep reducing meaning, like we deal in meanings such as irony or high-level constructs. But if you keep reducing any object of meaning down to its subparts, just less and less, you can start getting to very, very simple symbols and very simple meaning. So meaning is a symbolic relationship. Specifically, this object is like that object. In the case of self-referential meaning, one would recognize, for example, that this 2 simplex is like itself, or it is itself. So what is symbolic language or code? In other words, what's language? Language is simply the ordering rules and the syntactical freedom defining how you can arrange a finite set of symbols. And in the infinite universe of all possible languages or codes, virtually all of them use subjective or arbitrary symbols and ordering rules. You generally have to invent a language, except for quasicrystals. They kind of are this exception to that. And I've been looking for another exception, but have not found one yet. Quasicrystals are dynamical codes that are inherently non-local, and they're defined by various mathematics like C-star algebras and non-commutative geometry. And as with any language, these codes are non-deterministic not because they are random, but because they have syntactical degrees of freedom, where the syntax choices of geometric walks in the code cannot be predicted with certainty. You can only predict them probabilistically. So the logic of such codes is quantum Bayesian. And there are other algebraic formalisms that can describe quasicrystal languages, such as moduli space algebras, but no one has ever applied moduli space algebras to quasi-periodic arrays of points in a space. A quasicrystal should be thought of really deeply as a product of 2 objects. A higher dimensional lattice and its associated commutative and associative algebra, and then a package of vectors, in other words, a hypervector that operates or acts upon the lattice as a coefficient to produce a product, the quasicrystal. So the quasicrystal product, of course, is greater than the sum of its 2 parts, the lattice and the hypervector, because it encodes these things. It encodes, obviously, the lattice and its associated algebra, and it encodes the hypervector and its dynamics, because there's rules on how a hypervector can behave. So it can encode, dynamically it encodes the hypervector and its higher dimensional code, or walk rules on the higher dimensional lattice. And the product of these two coefficients, which gives you new objects that were not implied in either the hypervector coefficient or the lattice or algebraic coefficient. The objects that it encodes are of particular interest to us because we think that we can make a Hamiltonian out of one of these objects called the empire, and we can explain the QSN as a topological neural net. This is just a way to visualize Phazon dynamics in the Penrose tiling, which was created from the 5-cube lattice, Z5. So there's many, many different phases of Phazon dynamics. You can have local spinning particles. You can have propagators. It's kind of like the game of life with all these different propagators, except these propagators exist by geometric first principles. None of these look particularly particle-like because this is just some chaotic type resonances of a more homogeneous looking space. So a quasicrystal generated by an algebra or a lattice that encodes standard model gauge symmetry unification physics, such as E8, possesses physics that can be recovered with objects such as the Coxeter H4 folding matrix, where you can just basically map your object in the projective space. You map all of that. It's a completely different algebra, because down there, just as the lattice slice is transformed to a completely different object, the quasicrystal, as the product of the projection vector and the lattice, the algebra that represents the quasicrystal space is in some sense a product, or is a transformation by the operator product, which is the hypervector. So it's a more complicated or richer algebra, but what's interesting to me physically about the quasicrystal algebra is that it's non-associative and non-commutative. It's inherently non-local. So why and that's why you transform the E8 algebra in lattice in the first place. But there's a few reasons in addition. There are 5 reasons that this approach, Tony Smith is our friend, Carlos Castro works with us, and all these guys who've been thinking about the power of E8. And then, of course, in the 1980s, a lot of Russian physicists were trying to do unification physics on hypercrystals. And it didn't work. It faded out. There was a problem with that. It was as though the crystal was too simple. But the 5 reasons I suggest are, as I said, the quasicrystal algebra derived from E8. It's richer than E8 for the reasons that I explained, because it's a product of that algebra and a second algebra that defines the dynamical rules that control the hypervector, the shift vectors on the hyperlattice that act as coefficient operators on the E8 slice. So the product is simply a richer algebraic code. And Occam's razor is one good reason, because we don't have physical evidence that reality has 8 dimensions. We don't observe more than 3 spatial dimensions. And also smaller numbers and simpler things are generally preferable to more complicated things. What we have is evidence that reality is lower dimensional when its symmetry is broken at these energies. But we have mathematical evidence that the gauge symmetry unifications relate to higher dimensions, such as how a quasicrystal encodes higher dimensional objects and geometric objects and algebraic objects. The E8 lattice and algebra are not codes. If I give you the syntax right now of the Penrose tiling, and I give you the two tiles, and I put a pile of them on the table, and I ask you to build it out for me, you will notice right away that it is constrained by rules, but that it is impossible for me to predict the outcome deterministically of what you're going to build, because I can't predict how you will exercise your syntactical freedom in that geometric language. Now, if, on the other hand, I give you the tiles of a crystal lattice, and I ask you to follow those rules and build it out for me, well, then I can predict the outcome exactly, because it is not a code. You have absolutely no freedom. A quasicrystal algebraic code is non-associative and non-commutative. It is inherently non-local, and most importantly, there are powerful objects that we are exploiting called empires in quasicrystals that can explain quantum mechanics, we think, by geometric first principles. The most precise term for the code might be a topological quantum net. The dynamics of a quasicrystal algebra are reducible to binary or qubit-like states of points in moduli space algebras. This is interesting with respect to the code theoretic axiom and the principle of efficient language, because the simplest two objects are the empty set. The simplest two symbols are the empty set and the dimensionless point. Now, the point, as opposed to the empty set, can be used in geometric codes where it composites into higher dimensional self-referential geometric symbols, like a tetrahedron, okay, or a Gaussian polytope. In these quasicrystalline Phazon dynamical codes that can be modeled on moduli spaces, like our QSN. So now let's go back to the Planck scale quanta of consciousness idea and the measurement problem. Now, what is consciousness? Well, we don't know, and no scientists agree on it. We've gone to some of these conferences where quantum physicists and neurobiologists and these people come together and they try to deal with these problems. And they don't have any, they can't agree. They can't even agree on definitions so that they can start arguing in the first place. And that's not our concern, because we're not philosophers. We don't have to answer what is consciousness. So for our purposes, we just need a measuring and choosing operator at the Planck scale to comport more naturally with what quantum mechanics implies via the general measurement problem. And we might want to do some speculations in the future about how consciousness might emerge in the first place, even if we can't define it. And second, since we think reality is made of information, there's a reason why you need some notion of consciousness, because if we think reality is made of information, then you have to have an actualizer of the information, because information is just meaning generated by a word similar to observation or measurement or comparison or choice. It's a transformation in a sense, because every time you measure something, you're getting information about yourself, the sensor, and something about two or more irreducible points or objects that are out there that you're measuring. So it encodes information about your coordinate, and it encodes information about the relationship between the other 2 points. It essentially forms a transformation of an equilateral triangle in 2 dimensions, or in 3 dimensions, rotated to a 2-dimensional plane where any one of an infinite number of triangles can occur. So that is this triangle of the sensor and the 2 objects. And that encodes the information about the relationship of all 3 of those objects. So our approach, so analogously, you could just say that reality is meaning, geometric meaning, in our case, generated by syntactical choices or observations or measurements within a geometric code. Now, because our approach is reductionist, we're systems theorists, and we talk about complex systems and emergence. In fact, our theory is called emergence theory. But as extreme we are on systems theory and emergent complexity, we're equally as extreme in our attempt to reduce down into the irreducible things to where we can get no further reduction. Like you can't even imagine a further reduction. So we want to go both ways. So I can't accept the notion of randomness as the starting unexplainable axiom, because I don't have any physical existence that randomness exists. It's a conjecture. So the idea that there exists some universal random number generator for which we don't have an explanation is an unattractive axiom to me, because I'm curious. I just want to know everything. So I would rather look around and see with absolute certainty, do we have experimental evidence for randomness? And there's none. I can show you references on that if you're not familiar with why there's none. What there is evidence for is non-predictability and non-locality. And quantum experiments don't allow us to easily accept the notion of reality being a deterministic algorithm playing itself out. So that leaves us with only one option that seems interesting, the one deeply related to Conway's free will theorem and some of those deductions from the quotes by famous physicists earlier. Free will and some poorly understood notion of consciousness must exist as a fundamental mathematical operator at the Planck scale. Like randomness, free will is inherently non-deterministic, so it looks similar. Code theory-based physics, due to syntactical freedom, implies some sort of measuring chooser of the syntactically free actions, the probabilistic yet non-random behavior of this operator, this quote-unquote conscious operator. So how smart does such a choosing operator need to be? I don't know. I have no idea. How much like what we naively think of as consciousness does it need to be? I mean, maybe not similar at all. But we need this non-random mathematical operator in the code. There are logical, even if untrue, conjectures that one can think about in terms of how a universal scale consciousness made of these irreducible pixels of consciousness, these mathematical measuring choosing operators, how it could emerge. For example, you could ask yourself, well, what's the upper limit that physics imposes on the percentage of the universe's energy that can self-organize into conscious systems or into a network of conscious systems that is itself conscious in some sense, connected? Oh, well, of course, the most non-arbitrary answer to that question would be 100%. Like, that's less arbitrary than 79.3% of the energy in the universe can self-organize. And by the physical axiom, given enough time, whatever is possible physically eventually does occur. Well, by that axiom, then if this 100% number were the only logical guess, it's a guess. I mean, you just guess. 50%, 1%, 1/millionth of 1% is the upper limit that physics imposes. I don't know how many kilos I am, but I've self-organized into something that is this word that I don't know what it means, consciousness, and I make choices that you cannot predict with certainty, but that I do for strategic reasons relating to my stories and my theories. I want to go over here and get vanilla ice cream, you know? So if that's the number, or whatever the number is, somewhere ahead of us in a different space-time coordinate, this axiom would say that it's occurred forward of us in the same space-time object that we exist in. Now, if true, one can reasonably speculate on whether some new physics or even certain current interpretations of quantum mechanics, such as Bohm's view, where retrocausality exists. In David Bohm's view, it's retrocausal feedback loops are allowed. Because if you had a retrocausal feedback loop, a sort of connectivity as a four-dimensional neural network, topological neural net, then it gets really weird, because it means future states of that axiom, if something is possible given enough time, it eventually happens. It means that which has happened forward of us in time is retrocausally connected according to certain theories, interpretations of quantum mechanics. But that won't be answered since nobody can agree. It's been 100 years and there's still no good agreement on the interpretation of quantum mechanics. So I suppose that there will be no, I agree with Wilczek. I think there's got to be what Einstein wanted, but not entirely what he wanted. Einstein wanted some deeper explanation for why this probability theory. Why do things behave probabilistically like this? I want to know something else. And what he wanted was a classic idea of a deterministic algorithm playing itself out. He's not going to get what he wanted, but he'll get half of what he wanted eventually, I think. Somebody will come along with a first principles quantum theory that explains from first principles why the statistical probabilities. So retrocausality, as I said, wherein the substrate of a quantum gravity code, this graph drawing code that I'm saying is made of only information, that is the substrate. So that itself is the self-actualized, higher, emergent evolutionary that lives or is embedded within the ultimate self-organization of the universe that can hold an abstract object. Because think about it. Any of you certainly do not claim to be the ultimate evolution of a conscious entity according to the laws of physics. And yet you can hold within your mind the abstract information of a game of life, Conway's game of life. If you really had some photographic memory and you can imagine literally holding a simple cellular automaton model in your mind. The rules, the geometric connectivity of the space it operates on, right? Just as you can hold in your mind a cube. So that's bizarre, right? So in this view, the simple beginning of the geometric code is co-created by the self-organized evolution of the code forward in time, where it evolves, according to the rules, into a complex systems network, a sort of universal scale consciousness, for lack of a better word. And that emergent complex system is self-actualized and itself co-created by its simpler parts, the irreducible actions of measurement or syntactical action in the code itself. So when you come up to yourselves, an intermediary emergent entity within the code, and notice what you do all day. You make choices. And then those choices have to cascade down to the chemical level, the atomic, subatomic, Planck scale level, and somehow be interactive with whatever code lives down there. So you as an uber entity in there are in some sense like steering the cascade of simpler codes all the way down to the Planck scale. But the thing is if you have free will, okay, where you can have an algorithm that compels you to do all these things like eat, protect yourself from something, all the natural compulsions that are on you, and then all the natural compulsions of your belief systems and your theory and religious stuff. And then you could, if you want, arbitrarily do the opposite of everything you're compelled to do, just to test whether you have free will. And you still won't be able to prove that you have free will. But if you have that free will up there, then there's got to be something loose down at the bottom as it cascades down to the Planck scale. That is, that thing at the Planck scale logically should not be a deterministic algorithm playing itself out. So this is a fantastical idea, like just new age crazy idea. But on the other hand, it's only about as fantastic as the Big Bang itself, because that's fantastic. I'm not saying it's not real. I think the Big Bang is real, but it's fantastic, like an infinitely small point of energy self-organizing into us and this conversation. It's really weird. Or it's also as equally as fantastical as this Neo-Platonism idea that information just is. Don't know how, it just is. It's the primordial stuff. Or the remarkable strangeness of the retrocausal delayed choice, quantum eraser double slit experiment. That's weird. I mean, it's fantastical. It's just bizarre. So the idea that consciousness can keep self-organizing until it hijacks all of the energy in the universe and then eventually can be seen over space-time to be its own actualizer. Now you have a sort of causal loop that's logically consistent. A causes B, B causes C, C causes A, causes B. It's logically consistent, but you have to be open to the idea of Bohm and many others where somehow in a new quantum mechanics, retrocausal, or good interpretations of current quantum mechanics, that retrocausal feedback loops can be real. So anyway, at least it has the advantage of being logically consistent and fully explaining everything without any fundamentally unprovable axioms, because you turn it into a circle so that everything in that circle caused everything else. And in light of Conway's free will theorem and the principle of discretizing everything, the quantum of so you want to discretize that consciousness too. If you're going to go all the way, discretize everything, not just space and time and actions. So the quantum of such a consciousness-based substrate of reality, for me, would be a primitive mathematical code syntax chooser, the thing that I need to choose the syntactical freedom by some notion of measurement. A sort of quantum of consciousness that acts as a mathematical measurement or observation operator, such as a projective transformer, which actualizes the information of physical action and particles. For example, we think that each fundamental particle has its own projection window and projector. But up there, the projector operator has to choose because there's a few choices in its code that it could have made, but that you cannot deterministically predict. And that action, that mathematical action, is a measurement because it's a projection. It's a projective transformation. So this is the chart of how that would look. So you can pick any one of the 5 places on this chart and find a fully connected. There are really no axioms here because you wrap it into a circle. For example, let's take you, me, biological consciousness. Well, where did this come from? Well, it's emergent from space-time and particle physics. Everybody would agree on that. That's how our consciousness is here. But where did this emerge from? Well, we think maybe that emerged from a binary Planck scale, non-local code theoretic substrate, this moduli space of points. So where did those points emerge from? Well, this bizarre pan-consciousness substrate that is the inevitable logical self-organization of a universe where the upper limit is 100% of the energy. That's the hardest one to accept. So you get past this glitch on the circle, then you can say, well, all right, if that existed, well then, where would that come from? Well, then it starts coming around full circle. That comes from networks of consciousnesses exploiting the non-local code theoretic substrate. In other words, us and any other system, such as a cell in your brain, which has some primitive form of consciousness, right? It's a cell. It's like a little animal. It runs from, like the cells will run from predators. They'll run from noxious chemicals. They'll chase food, and they're completely unpredictable. They make these little stupid primitive choices, but they're choices. And they're choices for their own survival. Like they'll run, like a cell in your blood will swim this way or that way. And then big ensembles of those start connecting in a network in your brain and talking to each other, and probably are connected by some quantum physical models. And then this weird thing, like of Ray-Ashheim-ness, Ray-ness. And we don't know what Ray-ness is. But we just know that whatever Ray-ness is, his choices and his complexity of creating meaning and story are far more advanced and sophisticated than the single-celled organisms that team up to make Ray-ness, right? So the final part of the fundamentals that we work with in this sort of clean state or starting from scratch view of fundamental physics is the principle of efficient language, which I touched on already. Now, if you test drive this idea called the code theoretic axiom and you pretend that it's true, then an obvious question should emerge in your mind. if nature used a fundamental code, is that code included in the set of maximally efficient codes that are necessary to simulate nature? Now, even before defining efficiency, one can look to the principle of least action and all the other symmetries of nature that are imposed by Noether's second theorem, and one could easily conjecture, yeah, okay, it should be one of the codes in the maximally efficient set. Now, John Numrich published what I think is a seminal paper where he explored this question rigorously using probability theory. He tried to prove that if nature is a code, then the probability of it being any one of an infinite set of codes capable of simulating reality is ranked probabilistically according to his principle of least computational action. So it's a really interesting paper because of how mathematical and logical it is to say that if nature's a code, then a good way to approach fundamental physics is to start analyzing the efficiency of codes. So in attempting to define code efficiency, we might reduce it to binary actions or choices in the code itself. And a quasicrystalline-based moduli space code can be understood as, one, a possibility space of points that are arrayed in some space, where the algebraic code turns points in the possibility space on or off, or alternatively, it turns connections between points on or off. So that is, you can define a code's efficiency as the amount of physically realistic, Planck scale and above, dynamical pattern, physical modeling, that can be expressed on a graph drawing for some quantity of binary choices or actions in the code. Like if I give you only 1 million actions and you have to simulate physical system X, then the efficiency of such a code would be the one that simulates system X with as few binary actions as possible in the code. Now, as I mentioned, the code of the QSN is technically a topological neural net. So in light of the principle of efficient language, how would one begin ranking the efficiency of various neural network codes? So we believe that two concepts would be key to defining this and proving what is the most efficient class of codes. Connectivity is one way. So you can rank the connectivity of a network or a graph drawing by something as simple as the average valence rank. In other words, the average vertex degree is one way. So one of our outstanding problems for this year is to prove that the QSN is the maximally efficient graph drawing code in any dimension. Now, aspects of this proof are a little bit beyond the scope of today's overview, but it relates to sphere kissing problems. And then empires. Empires are absolutely key. Amrich's and Fong's presentations will get into detail on what they are. But there are special beams in empires or rays of points that drop in density with distance and that are very non-local. So to understand the role of an empire in this idea called the principle of least action, we have to start in one dimension, and you have to recall that word I gave you earlier called a possibility space. So the Fibonacci chain is a one-dimensional quasicrystal that's dynamical, and it operates on a one-dimensional possibility space that is itself a Fibonacci chain. So we decide to operate the code, let's say, on a finite possibility space Fibonacci chain by turning some of the points on and some of the points off in the possibility space in order to make a second Fibonacci chain that is scaled at some integer of the golden ratio relative to the possibility space. In other words, let's say that here I've just got this short Fibonacci chain possibility space that looks like this, right? And none of these points are on or off yet. It's the possibility space. So then if I say, well, I want to turn this one on, and so according to the rules, then this one would be off. And let's say this one is on and on. So by choosing this, you've made it impossible to choose this. So you can choose either one. And the distance on the first possibility space quasicrystal is your unit distance, where this is 1, and the shorter distance is 1 over phi. So you have 1 and 1 over phi. But then notice that when I operated my on-off values, I made the spacing bigger, so that these scaled up by a power of the golden one power of the golden ratio, where the power is always an integer number. So that's called inflation and deflation on quasicrystals. And a dynamical quasicrystal where particles propagate up and down on it, these non-local particles that have empires, that's called a Phazon quasiparticle. And all that is, a Phazon quasiparticle, is 2 or more legal states of the quasicrystal that are ordered in a legal way. So if I gave you guys a bunch of the Penrose tilings here, 100 pieces of the Penrose tiling, let's say that you could build with the 100, 3,000 different legal instances of that code with those 100 pieces. Now there's a second set of rules, which are the dynamical rules. So you cannot order those 3,000 separate Penrose tilings in any way that you want. You can only order them according to the Phazon dynamical rules. And then in that set, if you had 100 tiles, there would be a very large number of legal dynamical patterns that are coherent quasiparticle propagators on that. So the dynamical rules and the static construction rules. So we start arbitrarily with a single binary choice, a single registration of some point as being on in the possibility space. And so then by doing that, you would force a double-digit percentage of all the other points in the whole possibility space, which is called the empire of the first point. So you force them to be on, and another percentage you force to be off, and then another percentage, it's non-determined. It's syntactically free. So the remaining points, as I said, are the syntactically free points. Now, accordingly, there are up to an infinite number, if there's an infinite possibility space, of bonus points that are registered as on and off from that single action or choice of the first point being chosen. So the point is, what's the takeaway? You get a lot of bang for your buck. If your conserved quantity is computations or choices, right, because you're moving a shift vector, like let's say there's a shift vector up here in E8, and I'm projecting down to the E8 to 3D quasicrystal. So the language of this shift vector, let us say, gives you a choice. You can't change the angle, but you can change where it shifts to within the shift vector rules. And you could say, let's say there are two choices. And so therefore we say a binary choice in that code of just A or B lays down an infinite number of forced points in the empire of this quasicrystal in the lower dimensional space. Or you can stay in the lower dimensional space and operate on possibility spaces that are low dimensional, and then you arbitrarily pick some point to be on, and then that then gives you your forced stuff, your bonus registrations. So it's this unique thing that you get all this binary choices with a single action, a single choice, binary choice or trinary choice in the code. So a lot of bang for the buck if your buck is a binary choice. Alternatively, so I already said this. So quasicrystals are very unique in this regard, where binary actions generate very large quantities of automatically registered binary actions without actually using the resources that would be required on case-by-case choices of building out the empires. So let us hypothetically surmise that a Fibonacci chain code is the quintessentially efficient one-dimensional code because, for one reason, it has two letters, where those letters are two lengths as 1 and the golden ratio, and where this is the only ratio in the universe of all ratios with this fractal self-similar quality where the long part to the short part is the same ratio as the long part to the sum of the long and short. So when two Fibonacci chain possibility spaces are crossed in 1 plus n dimensions, then you actually double the number of bonus points. So let's say I turn a point, let's say I've got a chain in the possibility space with 1 million points, and I pick something to be registered as on, and then it gives me several 100,000 automatically included points as also on in the empire for that one price. Now, if I cross it with another Fibonacci chain possibility space that shares a point in the possibility space, then by choosing points on and off in either chain, it forces changes, it gives you bonus points forced on in both chains. So you double your bang for your buck. So, for example, when we cross these two Fibonacci chain possibility spaces that are very short and small with a second one, we can see how one binary action here will force changes on both of them. And if we only cross two spaces, the angle would not matter. In other words, you could do it at any angle. The two one-dimensional quasicrystals would still act as a network. But if we cross more than two, we must relate the spaces with golden ratio-based angles in order to have the whole network be connected and based on the same two letters. And then if we do this very small alteration from that angle, we will destroy the connectivity of the graph drawing space, and we'll introduce an infinite quantity of length symbols. So here where you see these introduced, that'll continue outwards, and you'll just have an infinite number of these points being connected. It'll start looking more amorphous, actually. So that's because the golden ratio, again, is the only fraction closed under multiplication and division that possesses that fractal self-identical quality that we talked about. So in terms of the principle of efficient language, the obvious question for nature then becomes, what is the maximum number of one-dimensional quasicrystals that can interact in a proper quantum topological neural net? Is there some upper limit to how you can network one-dimensional codes? So this is a little bit on the deflation-inflation operation. So you can take a Fibonacci chain as a possibility space, and it can be globally subdivided or locally subdivided. So this is inflation and deflation. So inflation is when you make the distance between points smaller, and deflation is when you make the distance between points larger. Those distances are based on Dirichlet integers, which are, like the fundamental Dirichlet integers are 1 and the golden ratio, or 1 over the golden ratio. So anyway, this is an example of an inflation where, or a deflation actually, where this is the possibility space where the distances are 1 in the golden ratio. And then we decide to turn certain points on and certain points off. So now the distances, the two letters here, become the golden ratio squared and the golden ratio. And we just achieve that by, say, folding this part here, and it will place a point here. It'll subdivide this distance by the golden ratio. Or you could fold that length from the other side, and it'll lay it down here. So these inflation-deflation operations on the QSN, where you start at the Planck scale, then all of your values are going to be essentially related to the power series of the golden ratio, like this. So you can do your local or global deflation inflations in any way that the code that we discover allows. So I'm going to refer in the rest of the talk to any local or global deflation inflation as just a Fibonacci chain. So I'm going to cheat on the definition a little. So if I had, normally when we say Fibonacci chain, it's made of only 2 letters in this golden ratio power series. But if we were to do it just locally and inflate a local portion or deflate a local portion, I'll still call that a Fibonacci chain. Now, we can think of, so this is what I explained. So any network of Fibonacci chains that composites into a 2-dimensional quasicrystal or a 3 or a 4-dimensional quasicrystal is a projection of a slice of an A, D, E, or Z n-dimensional lattice to 2D, 3D, or 4D. So if that's not clear, any of these special quasicrystals in 4D, 3D, or 2D can be thought of as a composite made from 1-dimensional quasicrystals based on the golden ratio. And any of those 1D, 2D, 3, or 4D quasicrystals is a projection of an infinite number of slices, because you can create, let's say, the Penrose tiling with a slice of any Z lattice greater than 4 dimensions. So Z5 on up, you can take slices and project it to the plane and generate the Penrose tiling. So the A, D, E, and Z lattices here are very fundamental.
Sorry, why do you, A, D, E, because you need simply lacedness, or for example, if you want something different like C, which is not simply laced, what happens?
Well, I take these ones as the fundamental ones based on the 90-degree and the 60-degree angle. For example, A, D, E, Z, their 2-dimensional facets are always either the equilateral triangle, yes, and or the square. So interestingly, there is a dimensional limit to networks of Fibonacci chains that relates to the fact that there are no 4+ n-dimensional analogs of the icosahedron and the dodecahedron. Some little bit of of crystallography terms would probably be good for us to share now. There are only 5, as you know, regular polytopes in 3 dimensions, and we can categorize those 5 into what I call the periodic and the crystallographic or crystallographic polytopes, which are the tetrahedron, the cube, and the octahedron. Regardless of the A, D, E, or Z lattice dimension, they can only be built from 3D facets that are the cube or a mix of tetrahedra and octahedra. The remaining 2 regular 3D polytopes are, of course, the icosahedron and the dodecahedron. These do not tile spaces, so they're not crystallographic, they're quasicrystallographic polytopes. So these 2 are related to the projections of n-dimensional A, E, D, and Z lattices, and of course their associated commutative and associative algebras. So these are the polytopes that cannot tile flat 3D space. These are the quasicrystal or the aperiodic class of Platonic solids. They have higher symmetry. And again, even though these quasicrystalline-based higher symmetry polytopes are the projective children, you can say, of higher dimensional simple crystal polytopes, the reason they are so rich and give you things like the Icosian algebra or numbers is because they are products of these simple crystal polytopes in higher dimension and a second parent or coefficient called the projective hypervector. So the number system that most naturally describes these special projections of the periodic lattices to n minus m dimensions are the Icosians, a subset of the quaternions that can describe the walks or the Phazon patterns in quasicrystalline objects such as the Hamiltonian or Eulerian circuits in quasicrystal-based polytopes, or the open walks that you would get in an infinite quasicrystal made of polytopes with icosahedral symmetry. Now moving on to 4 dimensions, we get one bonus periodic or crystal-based polytope called the 24 cell. And then we have the four-dimensional cube and the four-dimensional tetrahedron and octahedron, and then we have the two four-dimensional analogs of the higher symmetry regular polytopes in 4D, which is the 4D icosahedron and the 4D dodecahedron, the 600 cell and the 120 cell. And then it ends, just ends abruptly at 4 dimensions. So you have five in 3D with 3 in the crystal group, periodic group, and 2 in the quasicrystal group that are really generated by higher dimensional projections. And that's it. And then you go to 4D, and you have the same 4 in their 4-dimensional analogs, plus a bonus, the 24 cell, which is part of the crystal periodic group that you don't have an analog for in 3D. And so it's interesting because after 4D, the only regular polytopes are the periodic or crystallographic class, which is just the hypertetrahedron cube and octahedron to infinity. That is, you simply cannot have a network in 5 dimensions or greater that is based on icosions and the self-identical fractal uniqueness of the golden ratio. So quasicrystals based on the golden ratio can only exist in 1D to 4D. So this starts leading to some conjectures on why nature might be lower dimensional. Another way of saying this is that H4 is the 4-dimensional analog of H3 symmetry. So that's just icosahedral symmetry. So we published a paper, a cosmological paper that got accepted for publication recently, which is on quasi-periodic cosmology. And so we can do that in 4D and 3D. You wouldn't be able to really do that naturally in 5D because there is no analog of H3 and H4 in dimensions greater than 4. Again, quasicrystals are codes, first principles derived geometric languages that can describe quantized space-time and particles as patterns therein. So why would the QSN be the maximally efficient network code in any dimension? We cannot yet draw out a proof, but can offer clues supporting our conjecture that I hope later this year we will be able to prove why nature would use the QSN if she obeys the principle of efficient language. So continuing with the deductive process here, the principle of efficient language implies that nature would not have just one spatial dimension because obviously you can network Fibonacci chain codes in 1 plus n dimensions. She can get more bang for her buck, in other words, in terms of information generated for a given binary state selection on a graph drawing code. And nature would not use 5 dimensions or higher because you cannot network Fibonacci chains there, and therefore you cannot achieve maximally efficient quantum nets made of those objects. So it is trivial to demonstrate that the highest average valence rank in any 2-dimensional quasicrystal network is less than the highest in 3 dimensions or 4 dimensions. So I'm going to, without arguing that, I'm going to cast that out. So we're going to say nature would not use 1D or 2D because we suppose that those are not the maximally efficient network, where efficiency is defined by the maximal number of empires that can be generated from an interacting network of Fibonacci chain 1-dimensional codes. So that leaves only 3D and 4D as the candidates. Now, the E8 to 4D Elser and Sloan quasicrystal, that is the origin of our object, the quasicrystalline spin network, has vertices that are as high as degree 120. So valences of vertices that conjoin 120 edges. And so an E8 to 3D projection has valences that are as high as 30. So wouldn't this in and of itself, and both of these are networks of Fibonacci chains. project E8 to Elser-Sloan in 4 dimensions, you can construct that whole object as a network of Fibonacci chains. And project E8 to 3D, where you have vertices with valence as high as 30, that is also a projection, that is also a composite in 3 dimensions of partially inflated or deflated Fibonacci chains. And so wouldn't it be easy now to just simply make our first conjecture to be that, well, obviously the Elser-Sloan quasicrystal must be the most efficient quasicrystal code in any dimension, because you're going to get more bang for your buck, right? You're going to get more forced binary actions for any single binary on-off registration in the code, in the moduli space array of points in 4 dimensions. But not so fast. We discovered a novel object. We can take a slice of the Elser-Sloan quasicrystal in 4 dimensions that is centered on a 3-simplex, just a tetrahedron. And then we rotate 5 copies of that slice from one another in 3 dimensions to create a quasicrystal with H3 symmetry. If we use the rotation angle, if and only if, we use the rotation angle that the different 3-dimensional spaces containing tetrahedra are rotated from one another in 4D. So the Elser-Sloan quasicrystal has these 3D subspaces containing regular tetrahedra. Those 3D subspaces are rotated from one another by this angle, 75.522 degrees. So we use basically that same angle, but we cast out the 60-degree component of that angle for a reason that is deeply related to how the simplex series, so you can go up to E8 with just rotations of 60 degrees. So you can take a 1 simplex like this, and you rotate a copy of it on a vertex by arc cosine 1/2, right, to get the information of the 2 simplex. And then you can rotate a copy of one of those edges by the same 60 degrees to get the 3 simplex, which starts generating an irrational dihedral angle. So the dihedral angle of the 3 simplex generated by those 60-degree rotations is arc cosine 1/3. And then, once again, you can take a copy of the 3 simplex, the tetrahedron edge, rotate that by 60 degrees into the 4th spatial dimension, generating a new dihedral angle for the 4 simplex that is arc cosine 1/4, which is about 75.522 degrees. So notice that the generator of that process, which goes all the way up to the infinite simplex, is, and you can construct E8, by the way, out of 8 simplexes. And then it'll leave gaps, which are 8 orthoplexes, 8-dimensional octahedra. And then the conjoining of those 8-dimensional octahedra and tetrahedra in 8 dimensions forms the root vector polytope, the Gaussian polytope. And so anyway, so we cast out that 60-degree component when we use that same 4-dimension. So in other words, we're using the arc cosine 1/4 angle to arrange our tetrahedra in 3 space, which does something incredibly interesting. If you're a geometry geek, it's really a powerful thing that it does. It collapses. So if I were to take some tetrahedra and arrange them evenly with a shared vertex, then I would open up little gaps. So there'd be these little gaps at each of the 30 junctions between 2 edges on the outside. And so if you want them, and so the number of parallel planes in that object, that's the evenly distributed group of 20, which is not that picture, there would be 70 parallel plane classes. So when you do this rotation of arc cosine 1/4, which is how they're related in 4D, and then you cast out the 60-degree component, leaving only 15.522 degrees, which is expressed as 3 times the golden ratio minus 1, and then that divided by 4, and then the arc cosine of that. So then that becomes 15.522 degrees. So that expression, golden ratio expression plus arc cosine 1/2 equals your 75.52 degrees, which is the 4-dimensional rotation. Anyway, we take that remainder, the irrational component that's after the subtraction of the 60 degrees, we rotate these in 3D and we collapse the number of parallel plane classes here from 70 to the minimum possible, which is 10. Furthermore, we cause all faces to kiss, which is the only way you can cause the faces to kiss if they're sharing a center vertex. And thirdly, we interestingly divide each of the outside edges where the two outer edges cross. We divide each edge into the golden ratio. And if we arbitrarily choose to rotate it left, right, then we get this object. And if we arbitrarily choose to rotate left, we get this object. But it's the same set of points. So the 60 points here on the outside are really just graph connections. So if you make your graph connections this way, then you get the right-handed 20-group twist, with each of these edges divided into the golden ratio on this side. And if you arbitrarily choose left, which is just a different set of connections on the same 60 points that are static, you get the left-handed twist, which divides the golden ratio of those outer edges on the other side. So it's very analogous to what I showed you here, where we subdivide this very short Fibonacci chain possibility space into the golden ratio on this side or this side. This is just a not necessarily physically realistic example to help your visual intuition. Imagine a particle doing a Eulerian circuit in the QSN where these are 20 groups. And so I'll just play it and it'll speak for itself. So that's one of the 20 groups, and there are 20 groups everywhere in the QSN. And let's say that this was legal according to the Phazon Code that operates in one of the higher dimensional spaces like the Elser and Sloan quasicrystal. And so this particle is moving very, very fast. Let's say that it's the Planck time. So let's say that each frame is the Planck time. So that experimentally, if you take measurements of this, let's say that something like this were physically realistic at the Planck scale. Now, the fastest laser that we have is the attosecond laser that pulses at every 10 to the 18 times per second. Now, if you take something that's pulsing at 10 to the 18 times per second and you sample a process that's pulsing at 10 to the 44 times per second, what are you introducing into your data set? You're introducing randomness. In other words, it's physically impossible to take a 10 to the 18 sequence of, let's say reality is discrete all the way down to space-time. Therefore, time is simply an ordered set of frozen states on this graph drawing. So then if you take some equipment based on the apparent, on the chaotic oscillations of the metals in the crystal that are in the actuator that drive your attosecond laser, clearly every pulse of the attosecond at 10 to the 18 is not the same exact integer multiple of the Planck time as the one before. It's just a dirty, ragged, low resolution kind of pulse. And so then you would introduce, so then let's say you could capture, not that you can, but let's say you can capture the exact coordinate in an electron cloud, right, at these attosecond pulses. Well, you would get your data if it could show you the coordinates, and it would just be random. It would just be like a cloud all over the place because your experimental time resolution is not remotely close enough to do anything other than introduce forced randomness into the data. So what we do here is we're taking this E8 to 4D quasicrystal. We're using this special rotation we discovered several years ago to create this graph drawing called the quasicrystalline spin network that encodes the E8 physics, but has a remarkably higher power for encoding information than the ordinary projection of E8 to 3D, where you get, well, by the way, the valence of this is 60. So 60 points. Each one has an edge converging at the vertex at the center. So it's degree 60. The highest valence in the E8 to 3D projection is degree 30. So the average valence in the QSN is significantly higher than in the E8 to 3D projection. So this creates a three-dimensional network in the QSN of Fibonacci chains. In other words, the whole QSN can be built with just a bunch of one-dimensional Fibonacci chains, if you want to build it that way, with a very high connectivity rank. So describing what I described, which is how we make something called the compound quasicrystal. So the compound quasicrystal, so we project the Elser-Sloan quasicrystal to 4 dimensions. We take that slice that has an infinite number of tetrahedra. Here's a very, very small subspace of that slice. And then we rotate the entire slice in Mathematica relative to 4 other copies, 5 copies, by this 4-dimensional related angle that I told you about. And we collapse everything everywhere into this quasicrystal to have non-arbitrary closeness, a finite set of distances and vertex types. And if we didn't use that angle and we just rotated these slices by any arbitrary irrational angle, it would create arbitrary closeness. So going out, you would not have a code because you'd have an infinite number of distances and all sorts of different strange vertex types. And that object that I'm describing is a code-legal subspace of the QSN. So notice how the QSN is very dense and messy looking. You can't understand it because it's a lot of tetrahedra interpenetrating, and you can't make sense of it. But this compound quasicrystal made from the E8 to 4D quasicrystal, this is not close enough for you all to see, but these little red tetrahedra in here, or the blue ones maybe, can be thought of, the blue and red, they can be thought of as the code-legal subset of deflation-inflation operations maybe on the QSN possibility space. So the QSN, quasicrystal spin network, is the possibility space. The Elser-Sloan generated compound quasicrystal is a legal state selection on the possibility space. And you create quasiparticle patterns dynamically by legally ordering 2 or more of those selections on the possibility space. So it's a very on-off, kind of thing. Either a tetrahedron is on, according to the code, or off. And when they're on, they have this connection non-locally, which is through the empires. So the greatest vertex degree is still less. So you should still be saying, well, hey, Klee, so it's degree 60. So it's still a loser because the Elser-Sloan quasicrystal in 4D has degree 120 as the maximum valence rank. So that's probably has a higher average valence rank. And if the way you're defining a code efficiency in the principle of efficient language is to get the most bang for your buck on how many Fibonacci chains can cross, right? So that when you control one point, you control larger numbers of other points. All right, so why would nature use the QSN then, and not the Elser-Sloan quasicrystal if the principle of efficient language is true? 2 reasons make it a more powerful code, in my opinion. The QSN is chiral. So for every local state selection around a degree 60 vertex, there is a chiral mirror state that I explained to you here between the right and the left. So these degree 60 vertices that come in a double mirror set are ultimately derived from the degree 12 vertices in the E8 to 4D quasicrystal. So when you go from E8 in the E8 to that's a typo, 3D. So you project the E8 to 3D, you get some vertices that have a valence rank of 12. Okay, so that's 20 distorted tetrahedra, golden ratio distortions, coming together so that each edge is shared by 5 other edges, so that there are 12 vertices on the outside, 1 point at the center of the icosahedron, and a rank of 12 on the vertex degree. In the QSN, you can think of as saying, all right, well, we're going to force those 20 tetrahedra to be regular. We won't allow them to distort. So this is a talk Fong will give called geometric frustration. So you can express curvature, quantized curvature, as either a distortion under projective transformation to express the geometric frustration that exists between a 4D projection forcing itself down into lower dimension where there's not as much vectorial freedom, and things have to distort to release the pressure. Or you can just rotate things to express the exact same information. So again, that's a paper we did recently that Fong will go over. But what happens then if you force those 20 tetrahedra to be regular and then you rotate them in the way I showed? What happens is it's like a flower, like a lotus flower opening up to where a smaller set of vertices splays out to where each vertex of the icosahedron becomes 5 vertices as the flower opens up and becomes where 12 becomes 60. So now we're starting to see that it's not so easy to say that the Elsner-Sloan is more powerful, because here in 3D we have this chiral mirror state, which is different graph combinatorics on the same object. So it's not so simple yet to say. And the second reason is a little more difficult to explain with just this one slide, but it's in a paper that we published a few years ago. So it encodes information along the so the QSN is full of helices. And these helices are, in some sense, more numerical than the direct geometry of the Fibonacci chains, where we're just dealing with long and short, or we're dealing with tetrahedra. For example, one can encode a completely separate regime of information based on numerical sequences of 3 and 5 periodicity of these helices acting as numerical Fibonacci codes, where 3 periodicity maps to 1 and 5 periodicity maps to the golden ratio, right? Because remember, the golden ratio codes are 1 and the golden ratio. So again, this is explained in detail in this paper that we wrote, but the gist of it is that if I take a tetrahelix, because of the irrational dihedral angle, it has no periodicity. That is, if we have an infinite number of tetrahedra in a tetrahelix, it will never repeat. No 2 tetrahedra will have the same orientation. But if we apply the 15.522 degree rotation in the direction of the helix, so a helix, of course, has an absolute and non-relativistic helicity, right, of right or left helicity, irrespective of the observer. So in this case, let's say we have a right-handed tetrahelix with no periodicity. When we take our 15.522 degree golden ratio rotation between the faces, we collapse the periodicity from infinite periodicity to 5 periodicity. And if we rotate the same value in the negative direction, then we collapse it to 3 periodicity. And so assuming that the code of the QSN, which, by the way, we don't know the code of the QSN, but assuming that but we know it's related to the first principles of the way that the shift vector can move in higher dimension. But in any event, if the rules allow you to play with the chirality choice, this second binary choice that is not normally available in an ordinary projected quasicrystal to 3D, then we can encode a completely bonus regime of information in the periodicity, the numerical regime. So these 2 novel additional encoding schemes of chirality and periodicity, right? The chirality with the mirror state and the periodicity encoding power, they act, you could say, combinatorially with the other existing encoding schemes of an ordinary quasicrystal and with each other as coefficients in some sense, so that you really have an explosion of information possible with the QSN, in my opinion, relative to the E8 to 4D quasicrystal, where you may not have these same qualities. Now, whether that's true, whether it has those qualities in 4D or not, it's not clear. Whether this logic here is in the right direction is not clear. But it's enough for me to really appreciate how geometric frustration in 3D allows you this opportunity to create an incredibly rich encoding scheme. So I want to talk a little bit more about encoding soon with Fibonacci languages. So this makes it clear, at least at the pre-proof conjectural state, that the QSN should be the most efficient non-arbitrary, or that is non-invented, topological neural net code in any dimension. We cannot have a maximal vertex degree any greater than 60 in 3D, achieving this maximal vertex in the way we discovered generates the bonus encoding. Okay, that's typos, but basically this proof that I allude to that I want us to work on this year that relates to sphere packing problems in 3D, we don't think that you can get a vertex degree greater than 60 in 3D, period. If it is a network of, if you want it to be a topological net with the minimal set of letters, right, which requires it to be based on Fibonacci chains. So this, and if we can prove that, like I have a lot of friends like Stephen Wolfram, who's kind of interested in our program, and he is very interested in proofs like this. Like, can you prove from some rigorous first principles why a graph formalism in some dimension would be special or why it would be maximally efficient? So I hope to, I feel it would be important for us to allocate resources to try to formally prove that, because then we'll get a lot more attention, I suppose, from people in the loops community, from others outside, interested in the information theoretic view of reality that's becoming so popular lately. Now, Fibonacci chain is a geometric object that encodes another object, which is called a Fibonacci word. Now, a Fibonacci word is a sequence of zeros and ones that encodes one unique integer. So, for example, this sequence of zeros and ones would encode this unique integer. And this sequence of zeros and ones, where 1 is the golden ratio and 0 could be 1, for example, would be isomorphic to a Fibonacci, or at least analogous to a Fibonacci chain, a geometric object created by transdimensional, projection. So the usual Fourier space of each of those Fibonacci words that I showed you, those quasicrystals, so it's a numerical quasicrystal. So these numerical quasicrystals are represented by these non-chaotic looking geometric plots, which is the plot of the Fourier transform of the Fibonacci word. And now if you make a very minute syntactically legal change in this Fibonacci chain numerical quasicrystal, such as a single Phazon flip, which is a minute change just somewhere in the code, it's really beautiful because it creates dramatic phase shifts in the dual space representation on the plane. So that a tiny change changes it from this to this in the Fourier, in the plot of the Fourier domain space. Now, Mandelbrot said that the most complex object in mathematics, the Mandelbrot set, is so complex as to be uncontrollable, in other words, not understandable by mankind, and is therefore describable as quote-unquote chaos. The full Fibonacci sequence is encoded in the number of spokes on the bulbs of the infinite Mandelbrot set. And of course, the Fibonacci sequence converges to the golden ratio. So there's a deep connection to the Mandelbrot set to the golden ratio and via Fibonacci numbers. Now, when the Fibonacci word sequence of the zeros and ones is a Fibonacci number, the Fourier plot is the famous cardioid geometry of the Mandelbrot set, and it's not clear to me why. So this is the Fourier plot of those Fibonacci words in the images that I just showed you when the Fibonacci word is itself a Fibonacci number. So the number of zeros and ones is a Fibonacci number. So I superimposed that plot obviously onto this. I mean, it's just, it was not expected. So if the QSN is the basis of physics, and if it's just ontologically abstract information, in other words, if we say the QSN is information, well then any purely isomorphic space to that information, such as its dual Fourier space, must therefore be equally physical and perhaps even interactive with the geometric dual space of the quasicrystalline spin network, right? Once I plunge into the world of believing that reality is information theoretic, then if I ever thought that some formalism was ontologically used by nature because it's the most efficient, then anything purely isomorphic to that, for me, must be equally physically real because it's also the most efficient. And so I like the idea of dual spaces and this notion that other physicists have worked on of interaction or interresonance between the two spaces of a dual space. And obviously one thing about the Fourier space is it's deeply non-local. So if one analogizes each of these two-dimensional Fourier plots in matrix formalism, then we might consider the topological quantum superfluid, because the QSN behaves as a quantum superfluid. And so then maybe you can kind of visualize the QSN as an interresonating tensor network of these matrices, where each matrix corresponds to a one-dimensional code that's oscillating according to its rules and can be represented as a matrix. And then the interaction of all the one-dimensional codes is a tensor network of such matrices. And because a quasicrystal is a dynamical object with quasiparticles propagating through it, and is also an algebraic code that defines the Phazon dynamics, well, therefore, a dynamical Fibonacci chain is sort of like a sparkling and orderly aperiodic sequence of large integers. So you imagine this three-dimensional thing of these interacting one-dimensional codes, which are numerically the Fibonacci words of zeros and ones, which can be thought of as, if you want, as a tensor network of matrices. But ultimately, in one way of looking at it, it's this interacting slide lock, like this 3D Rubik's Cube kind of thing of these sliding integers or changing integers. So sliding, where you can say, well, on an infinite Fibonacci chain, so there's only one infinite Fibonacci chain. So any finite Fibonacci chain creating dynamism is just simply sliding that finite part along the infinite part to find the exact idea. Kind of like how your birthday or any number is somewhere along pi, for example. In the same sense, any finite quasicrystal or legal state, like we talked about the 3,000 legal states of the Penrose tiling that you guys could build here on the table, that each one of those 3,000 objects is just simply some coordinate locally in the infinite Penrose tiling. So it's as though these relationships between these local, the relationship between the different one-dimensional codes is in one sense, could be analyzed very numerically as this interactive code of large integers. So maybe the QSN is a dynamical network of these interacting integers, like a vibrating network of nonlinear feedback loops that overall behave as a topological quantum net. So ourselves and Cambridge Quantum Computing will be betting several $1 million on the conjecture that this same code that obeys the principle of efficient language is the discrete substructure of space-time, and that what defines the completely unknown natural limit of quantum computational power for n atoms. In other words, as I said at the beginning, nature should impose a limit. If you had 100 atoms, there should be an upper limit on the amount of quantum computation that can be derived from some arrangement over time and space of 100 atoms. And how can you guess at what that upper limit is without having a fundamental first principles quantum gravity theory? And so I would suppose that the upper limit deeply relates to this upper limit, this limit imposed by the QSN, that the QSN uses the maximally efficient network of one-dimensional codes. This is a quick animation that's fun. So these are state selections on the QSN that are driven by moving our cut window through the Elser-Sloan quasicrystal. So can we stay with simple geometric first principles to explain Lorentz invariance? Because so far I'm being extremely simple, right? Implying that it's just something all geometric, where time is just an ordered sequence of these state selections, these different quasicrystals. But we need to explain the apparent invariance of the speed of light. So we would like to revisit here in our program the notion of the de Broglie electron clock. But we want to make his notion of the electron clock discretized. David Hestenes with geometric algebra also did a lot of work on a modern version of de Broglie's electron clock model. David's a friend of our group as well. There are really only two axioms or assumptions that would be standing in the way of even talking seriously about this. The first is the guess that space-time has no substructure and that motion relative to that substructure is logically impossible. So if I'm an electron and space-time has substructure, well then logically I can I can propagate relative to the substructure and therefore have a notion of absolute propagation relative to the substructure. But if we guess that space-time has no substructure and is smooth, then it's absolutely illogical to talk about anything other than relativistic propagation. So the guess that fundamental particles are dimensionless points is another assumption for which there is no physical evidence, but it's an interesting conjecture, but that's all it is. And that is one of the conjectures that stands in the way between this electron clock idea. So let's talk about that. Rejecting the first assumption, which is the smoothness of space-time, until it's experimentally proven, removes the block to the possibility that there can be absolute local time and propagation in space. And revisiting Patti and Salam's notion from 1974 that quarks and electrons are themselves composites of ultimately fundamental point particles would allow for the notion of literal geometric stepwise particle spin in a graph drawing. And so we reject the notion that space-time has no substructure. Most of you probably know the Michelson-Morley experiment only ruled out a certain naive Aether theory, and it did not rule out discretized quantum superfluidic Aether theories. I mean, quantum mechanics didn't even exist when they did the Michelson-Morley experiment. And there is certainly no physical evidence against the notion that quarks and electrons have point-like substructure. I mean, that whole model was rigorously discussed by Paddy and Salam in the 80s and 70s. It's called the Prion model. So massive particles in the QSN have two forms of rotation in our view, which is a toy model at this point. The discrete stepwise spherical cycles, like the Eulerian path that I showed you with the purple animation. So those are spherical cycles of the particle's clock, like a modern version of the de Broglie electron clock, where you have spherical cycles of a particle that each full cycle describes a tick of the clock of that electron. And then a forward circular helical propagation, because the only way to logically move things forward in the QSN, because they're constructed of tetrahedra, is by helical pathways. So things propagate helically, but the pitch, I mean the width of the helix is very small. So it's at Planck scale in terms of that, but there would be a minute helical path, and that helix can take on different widths and different pitches, as would be allowed by the rules, which would be inflation, deflation. So the values of pitch that it can take and the values of the width of the helix would also be essentially the golden ratio power series. So now we have these two forms of rotation that have to be composed of these irreducible state selections, these binary actions in the graph drawing. The combining of these two rotations should require 720 degrees before the particle makes a full rotation, because half of the discrete spherical clock steps, the steps that, like imagine that there's this has to be visualized, I guess. Imagine that I'm spherically rotating a baton, right? Yeah, there you go. In a stepwise fashion, so it's chunk, discrete, just chunk, just states in the graph. And let's imagine that it takes 10 graph selections. I have to order 10 frozen objects in an animation to create one tick of the particle's clock. So if I have only 10, I cannot propagate it at the same time. But if I had 5 of my steps for the helical stepwise propagation and 5 of my steps for the particle clock, then I could split it down the middle, and I do less time. So the particle would measure other particles around it relative to its own clock time. But it has to be inversely proportional, and it's always, in our model, either, let's say you have 100 frames, you can spend all your money, your Clifford rotors, like you can describe them with Clifford rotor actions on the graph, or you could describe them with what we call trits, which is a trinary choice where a given tetrahedron is either on right or on left or off. So you can describe it that way. But if it's also helically propagating forward in this inversely proportional relationship between propagation and local particle clock time, then some of the steps of some of the Clifford rotors are actually moving in a direction opposite. Half of them are moving in a direction opposite of the vector or the direction of propagation, and then half of them are moving approximately in the direction of propagation, such that you would get a strange result of needing 4 pi in order to express the particle cycles. Hand waving, but the general idea. In special relativity, propagation and time, of course, are inversely proportional. In the QSN model, let us say you are given 100 discrete Phazon flips or Clifford rotor actions or spin actions on the graph drawing of the possibility space. Now you have to have an integer ratio, therefore, of spin quanta used for propagation versus spin quanta used for internal clock cycle steps such that there is a symmetry between propagation and the experience of the particle's time. Accordingly, the particle, or a human-level system of particles in the same inertial frame of reference, would measure other propagators relative to the absolute and non-relativistic ratio of its frames or spin actions that are used for propagation through the QSN versus clock cycles. The final element of this rough overview of our concepts is the notion of trit, parity, and anti-parity to describe repulsion and attraction. So again, a trit is on right, on left, or off for a tetrahedron in the QSN according to strict rules and syntactical freedom defined by cut and projection first principles. Now, each tetrahedron on the possibility space of the QSN can be in one of these three code legal states that we described. And remember, the empire is the bonus registrations of on or off made when the system computes or chooses one point in a quasicrystal, or one trit, one tetrahedron. In the QSN, each point selected that as on has to be a member of an equidistant set of 4 points. Has to be a tetrahedron. And as a result, we think that it's more computationally efficient to select entire tetrahedra as the irreducible quanta of space-time in the code, instead of having to make choices for each of the 4 points. Just choose the whole tetrahedron, since they have to exist in packages of equidistant 4. So this makes it for us a trinary instead of a binary formalism. And just as a point being on in the QSN has an empire of bonus points that must be on without having to use code choice resources, so too does a given trit state selection have an empire of tetrahedra that are forced to be on when you select one tetrahedron to be on. The discretized quantum field around a massive particle in the QSN is complex, actually, due to those two forms of rotation of the particle. This stepwise spherical combined with this stepwise helical, where there's no such thing as an electron at rest, so every particle is some integer ratio of propagation steps to clock rotation. But each of those two forms of rotation spews out an empire wave dynamically. So this empire wave of the particle and predictions about empire wave physical interactions can only occur probabilistically due to the non-deterministic nature of the code. So via geometric first principles related to this cut and projection geometry, the empire field drops in density with distance. So there's special dense beams within the empire, so that if you look at the Penrose tiling and we look at an empire, let's say this is a tetrahedron or a Penrose tile you select to be on, and around it you have these other things that are selected to be on, called the empire. Okay, and you have some interstitial spaces that are less dense with forced tetrahedra or forced tiles. So there's these beams or rays, certain certain cylinders, you could say, of forced tiles that are denser in those volumes in a 3D quasicrystal than the interstitial volumes. In other words, these empire rays drop in density with distance. And so when you try to visualize the complexity of an empire in 3D, which is not like, which would just be coming out in 3 spatial dimensions, and then you imagine that empire itself is rotating spherically while it's propagating helically. So those two behaviors and the ratio between them of the empire wave is what defines the the empire wave around a massive particle that goes to infinity if you have an infinite QSN, but it drops in density with distance. So now let's say we have a preon type of particle in the QSN at coordinate xyz at frame number x, so xyzt, right? Where time here is just frozen sequences of states, ordered sets. So so this particle has been propagating along some direction at a constant ratio of trits or Clifford rotors or whatever you want to use that are used for the clock cycle versus propagating in this Planck scale helical object. So now let's say it's a right-handed fermion. So this is a particle in the QSN that's based on right-handed trit selections. Now it's going to repeatedly use a certain chirality because it's a right-handed particle. And this creates an on-right trit field around it that drops in density with distance from the object. Now, let's say now there's a second particle that draws close to the first particle, and it has a trit empire field around it. So now what happens is the probability will increase as distance decreases for there to be a trit parity or anti-parity interaction in these two discrete fields. So this means, for example, that if Ray and his empire field, assuming Ray is a particle, in some frame of the global time of the QSN, this global ordered sets, so if Ray requires an on-right trit way out here at coordinate xyz, and then Mike's field, at a different coordinate, he requires an on-left trit at this same coordinate. Let's say I'm between them and I'm the coordinate. He needs an on-right, Mike needs an on-left. So now there's going to be a deflection because there'll be a trit anti-parity event between their two fields where they're competing for that trit. So there'll be a repulsive action or a deflection. Now, if on the other hand, Ray and Mike both need an on-right trit at coordinate xyzt, well, then there would be an efficiency in the code that is exploited because they both use the same object to express part of their structure, their field structure. So now both empire fields can economize by using the same trit at xyzt. And this will result in an attraction. The physical result is an acceleration or an attraction. That's it.